Hello, boys and girls. So I started the recording actually twice before, and I always got into a rant. So this time, I warn you up front. The first 2 minutes of this video will be a little bit ranty, but this is also a very light-hearted video. I don't even know really what I should title this video because it's just a small insight. It's not even particularly super smart or anything, but I just had to wrestle with it for a few minutes, and then I worked it out properly at home, and I thought I will go through that and present this to you. So there's this thing that came up. It concerns basically a family of distributions and concerns where the probability mass is. I will describe it in this video a little bit later, but it showed up in this book, Partial Differential Equations by Joost, third edition, where there is an average over some operators concerned, and then there's some epsilon delta proof, and I was like confused. Why does this go to zero? And so I will talk about this later, but I just want to motivate what kind of video this is here. Like, it's an explainer, but it's not like a topic that you would find in a book. Probably it's just some insight, and maybe if you go through with this for the next 15 minutes or so, then you would have also a little bit a reference point if this ever becomes a problem for you. The video at the moment has this paper in the background. We're not talking about this background at all, but this sort of cheeky title describes sort of this quintessential math thingy, right? Where the paper is called "A minus sign that used to annoy me, but now I know where it's there." And in this case, this popped up while I was reading the book. I was like confused for 2 minutes, and then I resolved it. But it's also this kind of, but is it really so? And then you work it out, and then you get it, and then it sticks far longer with you because you can always remember. Oh, there was a second where I was flabbergasted by this, or stumbled upon over it. How do you say, you fell over this small thing, but then it's kind of, you are enlightened more, and I hope this video contributes to that, or it's just a conversation. So with that said, I will shortly describe the scenario where this happens, but before that I introduce the main player here. We will talk about families of distribution, probability distributions in general, but the way in which this pops up in this book is with the exponential distribution. I will start here. So in the next few minutes will also be super basic. You might want to skip this if you know it, but maybe it helps if you stay with me and hear my, like, this is like a 101. What is this object? It will be of relevance later. So if you take the exponential e to the minus and then the parameter, then you have this curve which falls off, right? And the domain that we're going to use for densities in this video is the positive real numbers, or the non-negative real numbers, really. And if you have this exponential curve, here e to the minus x divided by whatever constant unit, in this case 0.1, and you want to make this into the probability density, where of course the integral over the whole positive axis is going to be 1. Then it turns out that exactly this parameter is also what you have to divide. This thing is perfectly normalized to 1. This works for every parameter m here. And so for 0.1, I also plotted here. So the blue line is the exponential fall off with this parameter set to 0.1 here. And the other example that I plot here is where this parameter is set to 0.4, which is here. And as it turns out, for the exponential distribution, this parameter is also the expectation of the distribution. So this is the mean of the distribution, right? So in a sense, in this sense of the mean, there's a bulk of a probability mass on the left side, a bulk of the probability mass on the right side. It's not the median. It's not exactly necessarily the half point. Like, I think it isn't. It might be, but in any case, it splits sort of the distributions right into two parts. And what you see here is that if you tune on the m, if you make it bigger, then the distribution becomes flatter because this mean wanders here. And so on the other hand, if you make it smaller, then it has to be steeper. There's another plot where I plot even more values. Here I plot all the values. The blue line is 0.1 again, and I plot various lines up to m equals 2, and this distribution look like that. I just tell you this because you should think of this distribution in the rest of the video, and this will all be about spoiler, that we're going to consider an interval from 0 to some value on the x-axis here, let's say that, and we ask, okay, where's the bulk of the mass? What is the mass of the probability distribution here? For example, for the blue distribution, there's a lot of mass between 0 and 0.5, whereas for this purple one, there's a lot less mass there. And the question that I ask myself, and which naturally popped up here, is if you have a sequence of points that moves towards 0 on the x-axis here, and you consider this as a shrinking interval, right? This shrinking interval, if you would fix the distribution, would capture a smaller and smaller part of the mass. If you at the same time move through a family of distributions, you change the family of distributions as you go along, then you can probably tune it so that the mass does not get lost. While the interval gets smaller, you at the same time you go to instances of the family such that more and more mass is concentrated in the smaller interval, so that you just save the mass. And in this video, we're basically discussing about how to intercorrelate the shrinking of the interval with the moving through the family of distributions, so that the mass you capture is maybe even constant, or at least, maybe in a limit you get all the mass in this interval despite you shrinking the interval, or maybe it gets lost. Maybe you move through the distributions too slow, such that when you move the point closer to 0, all the mass is actually on the outside. These sort of questions we are going to discuss in some formalities, and maybe later you have at least some examples in your head to see how, spoiler, you can basically tune it in a way that either this or that happens. And this was not so super clear to me how this looks in mathematical formal terms. So, okay, so how this pops up. Okay, here I define the probability distribution and the corresponding cumulative distribution function. It's the integral just of this thing. Okay, so far so good. So the thing where this popped up in this book is you have an operator t of a parameter s, and in this book I don't describe in this video at all what these operators are. They have to do with this diffusion, right? But you can think of them as the simplest, Lie type operator. They always look like this, e to the power of the parameter times some generator. And here in this first small calculation, I show you something what happens there, and you can just think of this as like literally just real numbers, e to the s times some other real number g. This thing has the property that if you go with s to 0, then this becomes the identity operator. It becomes the 1 in this case, right? And this will be important then for later in a second. So what is looked at in this book is a regularization of the difference of this of the operator from 1, right? There's basically this integral over this distance from how the operator looks for s equals 0, while how it looks for s, and you smooth this family of operators like so. And what happens if you compute this integral? That you can, in this case, this is so simple, you can do it by hand. You just have to know how to integrate the exponential function, and you get this kind of thing. And this so happens to be first order mu times g, and then no constants, but just terms which depend on even higher orders of mu. And so if you go with mu to 0, this becomes 0, the whole integral becomes 0. Okay, this is super simple. In the book, it's a little bit more complicated because this t is more complicated, but it also has the property, basically, so to speak, that if you go with s to 0, this becomes the identity. And you look at the same integral, here they insert a vector on which this acts on, but this just means that the integral is taken in some vector space. And so how they solve it is in this book is, because this, it's not just exponential functions, it's something more general. They have less properties to work with. But what they do is they take this integral and they split it up in two parts. One from 0 to some small delta, and from delta to the rest. And then what happens in the book is this. Because this difference becomes, you can intuit that it becomes very small, this difference, as s goes to 0, right? Because we said that the operator goes to identity, and so it's almost identity to identity, and this becomes 0. So this first part, 0 to delta, captures. So in the end, in the book, it captures the mass of the distribution, because you go for the family of distributions, but the difference is 0. And in the rest of the integral, the density is such that the density becomes 0, and so this part is also 0. So they even prove that both parts become 0, and so that's why the whole thing is 0. So what they want to achieve in this book is to show this integral becomes 0, and they do it by splitting this up. And here's where my confusion came in. I was looking at this proof, skimming over it, and then for a second I was like, okay, but is it actually the case that the mass lands on the left hand side? And in this proof, it's even simpler, because actually they do it epsilon delta. They don't even connect necessarily the mu and the delta. So if you look at it twice, you see, oh yeah, you can achieve this for sure. That you squeeze it enough to have the mass on this left side, and the left term is 0 because this difference is 0. But this is where my 2-minute confusions come in. I was like, okay, is it clear that the density of the exponential distribution lands there necessarily? And so I went home and I worked this out, coupling actually the upper bound, coupling the shrinking interval to how fast you move to the space of distributions, to the family of distributions, and this is what this video is about. I hope this explanation sort of makes sense. I just wanted to explain where this came from, my questioning came from. And now in the rest of the short video, in the next 5 minutes, you get just a little bit of more formalism at hand, and then you can use this and play with yourself and play with the speed of shrinking intervals. We're going to do it in a way where we have a parameter d, and we define an interval arbitrarily how it shrinks, and at the same time we have distributions which get squeezed, and then we can see, oh, we can actually play with it around such that the mass is inside of the interval even if we shrink it, or we can shrink the interval but move with the distributions too slowly and we don't manage to capture the mass, and it's just kind of nice. I hope that sort of makes sense, but we will see how this looks like. Okay, so just as a reminder, cumulative distribution function is defined like this. It has a bunch of properties, right? It's sort of S-curve. It starts at 0, it goes to 1. The probability density is the derivative of this thing. And then you can define these quantile values. You say, oh, I want to go on the cumulative distribution function, the probability P or Q, I call it here, Q, and this corresponds to some X values. And you say, oh, the mass up to this X value, if you would integrate over this X value, would give exactly the value Q. Okay, so now, and we are now abstracting far away from the exponential function. This is all completely general, just the fact that it's on the positive real numbers, but I don't use more than that. So now we're going to scale. We're introducing a parameter on the x-axis to scale just the x-axis. We're basically choosing the unit by which we want to measure the x-axis. This is very much inspired by this exponential distribution case where the parameter is mu. Now I have a more general parameter d. And here on this short page, I step into the derivation. What does this parameterization of the CDF mean for the parameterization of density, and you can do the analysis. If you take the derivative, you have to do chain rule, blah blah blah, and you get that the d pops up here twice. It's very much inspired by this exponential distribution again, and you know how to compute the expectation value in terms of how the situation looks at d equals 1, and also this quantile thing. So here again, if you choose q probability on the CDF, then it's very simple to compute the x value at which it will take the q, because it's just the scale the x-axis. It happens to be d times the original distribution that you squashed around. Okay, you can read this here in detail if it's not completely obvious for you. And here's the example that I generalized from, right? So for example, for the exponential distribution, actually, if you choose q, like, I don't know, 70%, 0.7, then to compute the x value at which it is actually minus mu times the logarithm of 1 minus this thing. Okay. So, and here to conclude basically the video already, what we will do now is we, previously we just said, okay, if I fix the q value, where's the x value at which this takes the thing? And we use basically the output value q of this CDF. Now we're saying what we actually control is the x value, right? And because we have this relation between this x value and the q value, the q value is basically the integral what you get from 0 to x, right? And so this determines how much mass is captured up to this x value. And we're going to choose an arbitrary parameterization of this x, some monotone interval shrinking function, right? The x value is we go from 0 to x, and we impose any sequence of x values by d that make for a shrinking interval. We have a fairly good generality here. For simplicity, the simplest function I could think of that is not completely trivial is we take d to the power of r, because if we let d go to 0, then this interval shrinks, and if the exponential is bigger, then it shrinks faster, right? Because it's like if r is 3, and then this is d to the power 3. If I step from with d from 1 to 1/2, then this goes down to 1/8 or whatever. Okay, so we control this parameter value such that the interval shrinks, and then just plugging in definition, integrating the parameterized density over this whole interval is given by this thing, right? And this is f without the parameter d, right? Here I use the fact that the fd was defined like this, right? We integrate over the parameterized probability density, we get this thing of our special value, and by definition this is x divided by this, and so we get, I hope you follow this, and so we get this integral is f of this right bound of the interval divided by 1d, so this is this kind of thing. So this looks a little bit interesting here, because now we see that depending on what the r is, if we shrink d, that this will either go to 0 where the CDF is 0, or it will go to infinity where the CDF is 1. I hope you follow my explanations here, or maybe it suffices what you see on the page here. But the thing is now that we can use this and play around with these and have different scenarios of what happens, right? So for example, if we go back to the exponential function case, we choose mu to the power of r, but mu equals d. This is just another letter that I use there. The integral from over this interval from 0 to mu to the power of r, right? The integral over this shrinking interval. It shrinks if I move mu to 0, this integral shrinks, but now even faster because it's to the power of r. If I integrate over this is this thing, and whether or not this goes to 0 or to 1 depends entirely on this r, right? So if the r is smaller than 1, then this thing is actually 1 minus e to the minus mu to 1 over mu to some positive number. And in this case, when you can now think of it, you go with mu to 0, this thing explodes, and you actually get 1. So in this case, just if this r is smaller than 1, then the relative speed of moving through the different densities and shrinking the interval of this particular speed has you capturing the mass of the integral in this small interval forever, which is the situation that you indirectly use in this book here. All the mass is on the shrinking side. Whereas, and this is now this interesting thing, if you actually take a bigger r, then this thing is positive, you go with mu to 0, and then this whole thing becomes 0. So in this case, you actually lose track of the mass. You shrink too fast, and the mass despite the probability densities being steeper and steeper, despite having this effect, if you move too fast with the shrinking interval, then you escape basically the mass, and the mass stays on the outside. This is what I intuited that should be possible, right? That you actually make this shrinking. You move through the space of parameter distribution not fast enough, so this, even if you shrink this, even if you move to steeper and steeper distributions, you actually do not capture the mass. This is what I wanted to say. Okay, this was a very messy ad hoc explanation, but I hope you get some formulas which you can play with. You can play with other intervals that shrink and see how do I actually have to tune for which speeds of walking through for making these intervals smaller and having this fixed family of distributions do actually capture the mass on the left or the right side. Okay, maybe this was a little bit over the place, but I hope you found this as enlightening as I did. So basically, the resolution to my question was, you can actually there's a lot of ways how this can play out, whether or not the mass lands inside or outside of this thing. Okay. I hope that was interesting to you, and I wish you a good weekend.